You might think of math as, numbers, equations, maybe geometry.
Right, the usual suspects.
But what if we told you that really, at its foundation, pretty much everything in modern mathematics is built from something surprisingly simple? The idea of a set.
It's true. Numbers, functions, you name it. It all comes down to these fundamental objects, these collections.
It's quite a journey, isn't it? From just intuitively thinking about collections of things.
Yeah, like a collection of books or something.
To these really precise, rigorous definitions that, well, they form the backbone of almost all mathematical thought today.
Exactly. And today, we're going to take a deep dive into those foundational concepts, the core ideas of set theory. We're using an introductory textbook as our guide, really laying out the groundwork.
Okay, so our mission for you, the listener, is to unpack these core ideas. Why did sets become the bedrock? How are even familiar things, like numbers, built from them piece by piece?
There are definitely some aha moments coming. It's amazing how simple ideas can lead to, well, incredibly profound insights.
And even different sizes of infinity, which sounds wild.
Oh, it is. Get ready.
All right, let's break this down then. We all have this sort of intuitive feel for what a set is, right? A collection of stuff. But why did mathematicians need to get so incredibly formal, so precise about it? It seems obvious.
Well, that's where it gets fascinating, because those seemingly simple, obvious ideas, they can lead you into deep logical trouble if you're not careful.
Trouble. Like contradictions.
Exactly. Historically, what we call naive set theory, just relying on that basic intuition, ran straight into paradoxes, real logical knots.
Okay, like what?
The text mentions a classic one. It sounds a bit complicated, but the idea is the least positive integer not definable in one line of type.
Whoa. Okay, say that again.
The least positive integer not definable in one line of type. Think about that frame.
Okay, it's defining a number based on how you define it.
Precisely. If such a number exists, well, we just defined it in one line, right?
Okay.
But its definition says it cannot be defined in one line.
Okay, I see. It's a self-contradiction.
It's a classic self-referential trap. And things like this showed that just using intuition wasn't going to cut it. You needed rules.
So the fix was to lay down really clear, explicit rules. Like a constitution for sets. Is that the axiomatic method?
That's exactly it. The axiomatic method provides a rigorous framework. It makes all your starting assumptions completely transparent. No hidden intuitions.
So statements only become theorems if you can logically derive them from these basic rules, these axioms.
Correct. It avoids the vagueness, the pitfalls of just relying on intuition. And this rigor is what ultimately allows us to embed, well, pretty much all of mathematics within set theory.
Meaning you can prove calculus theorems, algebra, everything just by talking about sets.
In principle, yes. It provides that unified, solid foundation.
Okay, let's get down to the basics then. In this formal world, what are the absolute core ideas that define what a set is?
Well, so fundamental principle is called extensionality. It's an axiom.
Extensionality.
It basically says this. If you have two sets, let's call them A and B, and they have exactly the same members, the exact same elements inside them, then they are the same set, period.
So it doesn't matter how you describe them.
Nope. The text gives an example. The set of prime numbers less than 10. That's 2, 3, 5, 7.
Right.
Maybe there's some complicated polynomial equation, and its solutions also happen to be exactly 2, 3, 5, and 7.
Okay.
According to extensionality, those two sets, the set of primes less than 10, and the set of solutions to that equation, are the identical set, because their members are identical.
So the how of the description is irrelevant. It's purely about the what's inside.
Precisely. The identity is purely in the contents.
What about the set with nothing in it, the empty set?
The empty set. Hugely important. It's denoted just empty braces. The text has a nice little analogy for it. Something like, a man with an empty container is better off than a man with nothing.
Huh. I like that. It sounds trivial, but I guess it's a necessary starting point.
Absolutely. It's a fundamental building block. You need nothing to start building something.
Okay, so we have sets defined by their members and the empty set. What about relationships between sets?
Right. We build up from there. You have the idea of a subset. Set A is a subset of set B if every single member of A is also a member of B.
Makes sense. Like 2, 3 is a subset of 2, 3, 5, 7.
Exactly. And then there's a really important concept. The power set.
Power set.
The power set of a set A, usually written PA, is the set containing all possible subsets of A.
All of them, including the empty set and the set itself.
Including the empty set and the set A itself, yes. Everything.
Okay, so if A is 1, 2.
Then the subsets are The empty set, the set 1, the set 2, and the set 1, 2.
So PA would be the set containing those 4 sets, 1 power.
And you got it. And there's a neat pattern. If set A has n elements.
Let me guess. The power set has 2 to the power of n elements.
Bingo. 2n subsets. That relationship 2n turns out to be incredibly important later on, especially when we talk about infinity. It hints at something deeper.
Okay. Filing that away. Now, thinking about numbers or coordinates, order often matters, right? Like 2, 3 is different from 3, 2.
Crucial difference, yeah.
But sets don't care about order. As we said, x, y is exactly the same set as y, x.
True. Extensionality again.
So, how does set theory, which is built on these unordered collections, handle something inherently ordered like an ordered pair?
Ah, this was a really clever problem to solve.
Yeah.
How do you define an ordered pair, let's say XY, using only the language of sets, so that XY is different from YX unless X actually equals Y?
Yeah, how do you do that?
The text points to a brilliant construction by Kuratowski. Defines the ordered pair XY as the set XY.
Whoa! Okay, wait, let's unpack that. It's a set containing 2 other sets.
Right, one set contains just the first element, X, the other contains both, XY.
And because sets don't have order within them, XY is the same as YX, but the overall structure.
The overall structure captures the order. You can always figure out which element came first by looking at the set with only one element inside. Unless XY, then you just have
That is surprisingly clever. It feels like a bit of a trick, but it works using just sets.
It's more than a trick. It's foundational. It shows you can build the concept of order from purely unordered components. It's a powerful demonstration.
Okay, so once you have a rigorous way to define ordered pairs, where does that lead?
Big places. First, you can define relations. Mathematically, a relation is just any set of ordered pairs.
Any set of ordered pairs, so like a set containing 1A, 2B, 1C, that's a relation.
Yep, that's a relation between the set 1, 2, and the set A, B, C. And then a function is just a special kind of relation.
How special?
It's a relation where each input element, the first element in the pair, is associated with only one output element, the second element.
Ah, the vertical line test for algebra.
Exactly. So in your example, 1A and 1C would mean it's not a function because one maps to both A and C.
Right, so that fx notation we all learned.
Introduced by Euler way back. In set theory, fx is just the unique y, such that the ordered pair xy is in the set f, the function. It all boils down to sets of ordered pairs.
Incredible. It really provides a unified language. What about other types of relations?
Very important ones are equivalence relations. These are relations that essentially capture the idea of sameness or similarity according to some specific criteria.
Like being equal.
Equality is the most basic one. But there are others. An equivalence relation has to be reflexive. X relates to X. Symmetric. If X relates to Y, then Y relates to X. And transitive. If X relates to Y and Y relates to Z, then X relates to Z.
Okay.
When you have an equivalence relation on a set, it naturally partitions or splits the set into distinct groups called equivalence classes. Everything in one class is related to everything else in that class, but not to anything outside it.
Can you give an example?
Sure. Think about the natural numbers. Let's define a relation where we say m is related to n if m minus n is divisible by 6.
Okay, so like 7 is related to 1 because 7, 1, 1, 6. And 13 is related to 1, 2.
Exactly. And 2 is related to 8 and 8 to 14 and so on. This relation is reflexive, symmetric, and transitive. It's an equivalence relation.
And it partitions the numbers. How?
It divides all the natural numbers into exactly 6 distinct equivalence classes. There's the class of numbers that leave a remainder of 0 when divided by 6, 0, 6, 12. The class with remainder 1, 1, 7, 13, remainder 2, 2, 8, 14, and so on, up to remainder 5.
Ah, I see. So it groups numbers that are alike, modulo 6.
Precisely. Equivalence classes are a super powerful tool for grouping things and abstracting concepts.
Which brings us to something really mind-bending. The idea that numbers themselves can be defined as sets. Is this just theoretical elegance, or does defining 0 as the empty set actually achieve something practical?
That's a fair question. It might seem purely abstract, but defining numbers this way isn't just a neat trick. It provides a foundational proof, from the ground up, for the consistency of arithmetic itself. It shows that the numbers we use aren't just arbitrary symbols we made up. They are rigorously constructed entities, built logically from the simplest possible starting point, the empty set. It grounds arithmetic in pure logic.
Okay, so how does the construction work? The text lays it out.
Yes, it uses a standard approach, often credited to von Neumann. The natural number 0 is defined as the empty set.
Okay, 0 is nothing. Makes sense.
Then, The number 1 is defined as the set containing only 0. So 1 is the set.
Right, the set containing the empty set.
Then 2 is defined as the set containing 0 and 1. So 2 is the set 0, 1, which if you substitute the definitions is...
Whoa, okay. It gets complicated fast.
It looks complicated, but there's a beautiful pattern. Each natural number n is defined as the set containing all the natural numbers smaller than n.
So 3 would be 0, 1, 2, which is then.
Exactly. It's this nested structure. And the amazing thing is, using just these set definitions and the axioms, you can rigorously derive all the rules of arithmetic. The text even shows how something like 2 plus 2 = 4 can be proven from these basic set operations.
That's profound. Building arithmetic from literally nothing but empty sets and the rules of collection.
It really is.
So if we can build the natural numbers 0, 1, 2 this way, what about the rest? Integers, rationals, the real numbers, do they also become sets?
Absolutely. The construction just keeps building layer by layer using the tools we've already developed, like ordered pairs and equivalence classes.
Okay, how do we get integers, including negative numbers?
Integers are defined using equivalence classes of pairs of natural numbers, mn. The idea is that the pair mn represents the integer m minus n.
Okay.
So the integer 2 isn't just one pair. It's the equivalence class of all pairs, mn1, where mn equals 2. Yeah. That includes 2, 0, 3, 1, 4, 2, and so on. They're all considered equivalent ways of representing positive 2.
And a negative integer, like negative 3.
That would be the equivalence class of pairs, where mn equals negative 3. So pairs like 0, 3, 1, 4, 2, 5 all belong to the class representing negative 3.
Clever. Using pairs of naturals and equivalents to get negatives. What about fractions, the rationals?
Similar idea. Rational numbers are defined as equivalence classes of pairs of integers, say pq, where the second integer q, the denominator, is not 0. This pair represents the fraction pq.
And equivalence handles things like 12 being the same as 24.
Exactly. The pair 1, 2 is in the same equivalence class as 2, 4, 3, 6, negative 1, negative 2, and so on. They all represent the same rational number 1/2.
Okay. Naturals from sets, integers from pairs of naturals, rationals from pairs of integers. What about the real numbers, like pi or the square root of 2? Those aren't simple fractions.
This is where it gets particularly elegant and really crucial for things like calculus. The text describes using Dedekind cuts.
Dedekind cuts sounds serious.
It's a brilliant idea. A Dedekind cut essentially defines a real number by partitioning or cutting the set of all rational numbers into two sets, A and B. Set A contains all the rational numbers less than the real number you want to define, and set B contains all the rational numbers greater than or equal to it. The real number itself is uniquely identified by that specific cut, that specific partition of the rationals.
So the square root of 2 is defined by the set of all rational numbers whose square is less than 2.
Precisely. That set of rationals is the Dedekind cut that defines the real number square root of 2. It pinpoints its exact location on the number line by specifying everything rational that comes before it.
Wow. And this method works for all real numbers, rational and irrational.
Yes. And critically, this construction using Dedekind cuts guarantees that the real numbers have a crucial property that the rationals lack.
Which is?
The least upper bound property. This means that any non-empty set of real numbers that has any upper bound, a number greater than or equal to all numbers in the set, must have a smallest upper bound, called the supremum, that is also a real number.
Okay, why is that so important?
It's what makes the real number line complete or continuous, without any gaps. The rationals have gaps like the square root of 2 isn't there, the reals don't. This property is absolutely essential for calculus, for limits, for derivatives, for integrals, basically for modeling the continuous world. It's the secret sauce.
Incredible. So we've built the entire number system essentially from scratch using set theory. But what about the size of sets? Especially infinite ones. My intuition says infinity is just infinity. Are all infinities the same size?
Intuition about infinity can be very misleading. Set theory gives us precise tools to compare sizes, even for infinite sets. The key concept is equinumerosity.
What?
Equinumerosity. Two sets, whether finite or infinite, are said to be equinumerous or have the same size or cardinality if you can create a perfect one-to-one correspondence between their elements. A perfect pairing with no elements left over in either set.
Okay, like matching fingers on two hands.
Exactly. Now, for infinite sets, this leads to some weird results. Galileo noticed this way back. Consider the set of all natural numbers, 1, 2, 3, and the set of their squares, 1, 4, 9.
The squares seem like a much smaller set, right? They get spaced out further and further.
Intuitively, yes.
Yeah.
But are they equinumerous? Can you pair them up one to one?
Well, you can pair 1 with 1, 2 with 4, 3 with 9, n with n squared. Yeah, you can. Perfectly.
Right. So even though the squares seem like a smaller part of the natural numbers, the two sets have the same cardinality. They're equinumerous. This is a classic paradox of infinite sets. A proper subset can have the same size as the whole set.
Okay, that's strange but makes sense with the one-to-one pairing definition. But then Cantor came along.
George Cantor. He took this idea and ran with it, completely revolutionizing our understanding of infinity.
He showed that not all infinities are the same size, right?
Exactly. That was his bombshell. Cantor's theorem proved it. He showed, definitively, that the set of natural numbers, whose infinite size, the smallest infinity we call Aleph null, written arrow, is not equinumerous with the set of real numbers.
So the infinity of the real numbers is bigger?
Yes, strictly larger. He showed that the size of the real numbers is actually the same as the size of the power set of the natural numbers. Remember the power set?
Yeah, the set of all subsets. Its size was 2n for a finite set of size n.
Right. So the size of the real numbers is 2 to the power of Ellis null, 2 arrow. And Cantor proved that for any set A, the power set PA is always strictly larger in cardinality than A itself.
Always. Even for infinite sets.
Always. So 2 arrow is strictly greater than arrow. There are fundamentally more real numbers than natural numbers. Different sizes of infinity exist.
How did he prove that? The text mentions diagonalization.
Yes, his famous diagonalization argument. It's ingenious. Imagine you could list all the real numbers between 0 and 1 in an infinite list. Cantor showed how to construct a new real number that is guaranteed not to be anywhere on your list by making its decimal expansion different from the first number's first decimal place, the second number's second decimal place, and so on down the diagonal.
So any attempt to list all the reals is doomed to fail, meaning you can't put them in one-to-one correspondence with the natural numbers, which can be listed.
Precisely. It proves A and 2 heroes are different cardinalities.
Mind blown. Okay, so we have different infinite sizes. What happens when you try to do arithmetic with them? Like, what's Aleph null plus Aleph null? Or Aleph null times Aleph null?
Here's another place where infinite arithmetic is totally counterintuitive. It turns out adding or multiplying infinite cardinals is surprisingly simple due to something called the absorption law.
Absorption law.
Yeah. For any infinite cardinal numbers, let's say k and l, where k is the larger one, or they're equal, and l is not 0, it turns out that k plus l is just k, and kl is also just k.
Wait, seriously? So RO plus RO is just R?
Yep. Think about adding the even numbers, size r's, and the odd numbers. Let's get all the natural numbers back, size r's. And r times 0 is also on.
Also R's.
You can arrange pairs of natural numbers in a grid and show you can still list them all, putting them in one-to-one correspondence with the naturals themselves.
So for infinite cardinals, addition and multiplication basically just collapse to the larger of the two cardinals involved.
Essentially, yes. Max, k, l. It simplifies things dramatically, though it feels very strange compared to finite arithmetic.
Wow. Okay. This brings us to the last major topic, I think. The real elephant in the room for set theory. The axiom of choice. It sounds innocent enough, but why is it so controversial?
The axiom of choice, or AC. It sounds simple. It basically says if you have any collection of non-empty sets, could be infinitely many sets, you can always form a new set by picking exactly one element from each of those original sets.
Seems reasonable, like picking one sock from each pair in a drawer.
Well, that's where the famous analogy by Bertrand Russell comes in. He clarified the issue brilliantly.
The one about shoes versus socks.
That's the one. If you have infinitely many pairs of shoes, Russell said, you don't need the axiom of choice to pick one shoe from each pair. You can make a rule. Always pick the left shoe.
Okay, there's a definable procedure.
Right. But if you have infinitely many pairs of socks, assuming they're identical within a pair, there's no general rule you can state beforehand to pick exactly one sock from every pair. There's no left sock.
So you can't specify the choice universally.
Exactly. The axiom of choice simply asserts that such a selection, such a choice set, exists even if you can't possibly describe or construct the rule for making the choice across all the sets simultaneously.
It's non-constructive. It postulates existence without providing a method.
Precisely. And that non-constructive nature is what bothers some mathematicians. It leads to proofs that show something exists without showing how to find it, which feels unsatisfying to some, and it leads to some very weird consequences.
Like what powerful, maybe counterintuitive things does AC allow us to prove?
Well, one major consequence is the well-ordering theorem. It states that every set can be well-ordered.
Meaning?
Meaning you can impose an ordering on its elements such that every non-empty subset has a least element under that ordering. The natural numbers, 0, 1, 2, are well ordered under the usual relation.
Okay. But AC implies you can well order the real numbers.
Yes, which is bizarre. Nobody's ever been able to actually describe or construct such a well ordering for the real numbers. AC tells us one exists, but we have no idea what it looks like. It's purely theoretical.
That is strange. And it's connected to that continuum hypothesis thing.
It is. The continuum hypothesis, CH, is the question of whether there are any infinite sets whose size is strictly between that of the natural numbers and that of the real numbers.
Is 2 error the next size up from 2? Is it LF11?
That's exactly what CH proposes, that 2 euro. Cantor believed it was true, but couldn't prove it. And here's the kicker. Gödel, and later Cohen, proved that CH is independent of the standard axioms of set theory, usually called ZFC Zermelo-Fraenkel axioms, plus the axiom of choice. You can't prove it true, and you can't prove it false, using the standard rules.
Wait, what? It's undecidable.
It's undecidable within ZFC. You could add CH as a new axiom, or you could add it to negation as a new axiom, and you still have logically consistent, as far as we know, versions of set theory.
That's a whole other level of weirdness. The axioms aren't powerful enough to decide the answer.
It tells you about the limits of our axiomatic systems. It's a profound result.
Wow. We've really covered some ground, from just thinking about collections to paradoxes, forcing rigor, building numbers from nothing, grappling with different infinities, and ending up with undecidable questions about the very structure of infinity.
It really is an incredible journey. It shows how mathematics builds this immense, intricate, and surprisingly consistent structure from what seemed like the simplest possible starting points.
And this deep dive hopefully shows how those just symbols in a textbook, they connect back to really deep ideas about quantity, order, and even logic itself.
Absolutely. And understanding these foundations isn't just for pure mathematicians. It really sharpens your thinking about how any complex system, any set of rules is built, how precision matters, how assumptions matter.
So what's the takeaway for you, the listener? Maybe next time you see a number or a graph on a screen, or even just think about a group of things.
Consider the hidden scaffolding, the incredible structure of set theory that often invisibly holds it all together.
And it makes you wonder, doesn't it? These mathematical structures, like the real numbers, seem perfectly continuous. But is the actual fabric of reality like that? Are the lines we draw in the physical world truly continuous, like the set of real numbers?
Or at some incredibly tiny scale, maybe reality itself is more granular, more discrete. Does it behave differently? It's that fascinating interplay between the abstract models we create and the reality they're trying to describe.
A profound thought indeed, the relationship between math and reality.
Definitely something to keep exploring.